Thank you for your interest and patience. I'm sure it's been a very busy and hopefully a very beneficial week for all of you. So again, thanks for hanging around at the very end of Ignite 2016. We'll make it worth your while. So hopefully many of you are SQL architects, SQL administrators, SQL developers, and hopefully you've had a chance during this week to learn about some of the great capabilities and features that we are offering in SQL Server 2016. Our session here is kind of tying all that together based on actual customer engagements. What we want to give you in this session is some of those practical use cases where we have seen these features being used, and also some of the practical considerations. You may call them gotchas, you may call them tips and tricks. That's exactly what we want to focus on today. To do that, we have Denzel Ribeiro, and I'm Arvind Shamsundar. We are part of a team called SQL Cat. Hopefully you know us from the community. We've been around for a very long time. But in case you did not know about SQL Cat, here is a very quick blurb about us. So we are a customer-facing team. We work within the engineering organization, but then we are working with customers all the time. And our focus is to work on customer engagements where there are pre-release software involved. Historically, this has been software such as SQL Server 2016. Of course, 2016 has been generally available for a couple of months now. So our immediate areas of interest, you can kind of see on the screen, are things like Azure SQL DB, Azure SQL Data Warehouse, but our core focus still remains SQL Server because that's what runs behind the scenes of even the stuff in the cloud. So of specific interest to us today is SQL Server on Linux, and I just want Denzel to talk briefly about that.
So we are running a private preview from the SQL on Linux perspective, and of interest is in particular those app stacks which are not already on Linux, and you have a workload that you're interested in testing. If so, please apply for the preview program, and you can reach out to me directly. My contact info is in the deck.
Thanks, Denzel. So again, just a quick shout. We do have formal customer engagement process. We'll show you how you can interact with us through that later on at the end of the slide. We have a customer lab in Redmond where we do offer customer engagements and so on. So just a quick blurb on our team in case you have not heard about us in the past. So today what we want to focus on, again, as I said earlier, we want to kind of put together a lot of the good stuff that you've already hopefully had a chance to look at earlier this week. So in-memory OLTP, column store indexes, temporal tables. Hopefully these are not the first time you're seeing these terms, and that hopefully you've had a chance to look at some of the sessions earlier this week. But again, as I said, we want to focus in this session on the lessons learned. And this is not something synthetic. We've actually been working with customers, adopting SQL Server 2016. We want to take those learnings and bring them back to you as best practices, lessons learned, gotchas, tips and tricks. So I will begin with a section around general considerations in SQL 2016 upgrades, followed by some scenarios around data loading in column store indexes. And then Denzel will take it further in the areas of in-memory OLTP, and winding it all up with a very interesting use case for temporal tables and how that actually blends together with column store indexes and in-memory OLTP as well. So to begin with, some overarching themes, and this is more conceptual, and a lot of it makes sense when you look at it, but we found this was a very common tripping point for customers. So just a broad set of considerations around when you're upgrading to 2016, what should you watch out for? So again, if you have not heard about 2016 at all or not worked on a lot of the features earlier, there are some great related content at Ignite 2016. Highly recommended that you either had a chance to look at them earlier this week, or you can take a look at the content once it's available on the Ignite website. So just 2 slides here, and then we will move on into column store. But we just wanted to emphasize a lot about when you are upgrading. A lot of customers are coming in from older releases of SQL, such as SQL 2012, sometimes SQL 2014, or sometimes even way earlier, like 2008 R2. A big thing you must keep in mind is behavior changes in compatibility level 130. So how many of you know what compatibility level means? Just a quick show of hands. Great. So you know that this is really a very critical knob, right? It controls the way the query optimizer generates plans and so on. One of the big things we changed in 2016, SQL 2016, is the availability of certain new behaviors / features is only available if you're using compatibility level 130. For example, we have some great stuff in the form of parallel insert select. I'm going to show you a demo and how this can rapidly improve your data loading performance. Only available in 130 compatibility levels. You have a lot more support for parallelism within memory optimized operations on memory optimized tables. Only available in 130. We have batch mode operations. Now, I'll talk a little bit more about that when we get to the column store section. At this moment, just imagine that batch mode is this mode of execution where we can use CPU much more efficiently and give you a lot more better performance. Again, a lot of those operations, for example, batch mode sort, window functions like rank, or you use lag or lead, all of these are only available in batch mode if you use compat level 130. So all of this is good, right? When you're developing a new system afresh, you can start with 130. But what if you are moving from a legacy system onto 2016 and you want to use this good stuff, but then what should you watch out for? So one key thing to watch out for is if you're jumping from 2012, which had a compatibility level default of 110, or even earlier, compat level 130 has a lot of changes for you from a cardinality estimation perspective. If you've never heard about cardinality estimation, basically it's one of the key components which the SQL query optimizer uses in order to make the right decisions about what's the best plan that I can use for this particular query. So the key message in this slide is, while there's a lot of good stuff exposed to you only under compatibility level 130, you must make sure you test the other parts of your workload adequately with this compatibility level 130. So very simple flowchart. When you look at it, it sounds so simple and common sense, but we had so many customers hit this around, oh, I moved from 2012 or even earlier to 2016, and my queries start behaving differently. In many cases, they behave positively. They improve in terms of throughput or performance, but in some cases, they do take a step back in terms of regressions, or query performance actually degrades. So very simple flowchart. This looks so obvious when you look at it, but I think this was ignored by a lot of our early adopters. So we would strongly advocate, when you're upgrading a database from an older release of SQL, we strongly advocate that you start simple with the compatibility level as it is. But then you use this great feature in 2016 called Query Store, which is essentially a single place where you can kind of record the performance of a query under different compatibility levels. So Query Store, when you turn it on, it starts recording what's happening on the system in terms of execution plans, how long they took, and so on and so forth. Then you establish your baselines, and then move forward by flipping the compatibility level to 130. And this is when Query Store gives you that visibility into what was the prior state and the change state. And again, how many of you have used Query Store or seen it in action earlier this week? Not too many, right? So I strongly recommend, there was a session exclusively on Query Store earlier this week. You take a look at that recording. But one of the great things in Query Store is it has a great UI embedded within Management Studio, allows you to very quickly detect which of these queries have turned bad, so to speak. And it also offers some method around forcing query plans, which allows you to go back. So again, I don't want to spend too much time on this methodology. It's pretty simple when you look at it, but believe me, it's important that you be aware and kind of follow through on this on a structured approach when you're upgrading. So again, in the interest of time, just a housekeeping thing is, if you can keep any questions you have towards the end, that would be really useful for us. But if there's something, feel free to use one of the mics for Q&A as well. All right, I'm going to get into what proved to be one of the most popular features in SQL Server 2016, column store indexes. Again, if you don't mind, a quick show of hands, how many of you have used column store indexes or have seen it in action? Good. So column store indexes as I mentioned, have been the most popular feature. It's been one of the most widely adopted features in SQL 2016. And the reasons for that, you will see in a minute, have been the fact that we really completed what started off in SQL 2012 as a read-only column store index, right? There's been a bunch of improvements. I'll talk about that in a minute. But The key positioning is, again, column store indexes start off as primarily oriented towards data warehousing type situations, right, where you have reporting needs and you want to run those off a huge set of data. We're typically talking about millions and sometimes even billions of rows. In 2016, we have enabled a couple of enhancements which allow you to do this in a more real-time basis. So Kevin and Sunil Agarwal in this conference have talked about operational analytics, and the key part of that is the ability to do things like additional indexes on top of clustered column store. So you can now combine the best of these huge queries which are rolling up lots of rows, and you have point lookups where you're looking at particular rows at a time. So that's one of the key things we enhanced in SQL 2016. We also added support for foreign keys and primary keys. Because we now have non-clustered indexes, we can actually lock specific rows rather than having to lock different groups of rows at the time. A very useful feature which was made available in 2016 as well is the ability to start reading from these column store indexes on replicas. If you use always on availability groups in 2016, you can actually have read operations from these column store indexes. This is such a cool feature because it now allows you to do true read only scale out on your replica workloads. And then some of those enhancements I mentioned in the previous slide around compatibility level 130, batch mode operations and so on, we have a bunch of those specifically targeted at column store indexes themselves. Now all of this is good in terms of enhancements, features and so on. What did customers find? And I just want to zoom in for a minute and try to highlight a couple of these key things. This is a diagram which actually shows you space savings when we are dealing with column store indexes. Now column store indexes were actually designed with performance in mind, but they have this great side benefit of saving you storage space as well, right? Especially when you use clustered column stores, because there the data is itself super compressed. The diagram there basically walks you through three progressions. The column on the left is a page compressed table. It has 3 billion rows in it, and the size of that table after page compression was 500 odd gigabytes. The third column in that diagram there is the same table, 3 billion rows worth of data, with a clustered column store on top. And that actually reduced to around 160 gigabytes. So you have the significant savings even on top of conventional page compression, which is itself quite efficient. So the key message here is, in addition to any performance benefits that you are looking for in terms of queries which are running on this data warehouse type data set that you have, space savings have been proving to be very, very popular benefit of column store indexes. And when it comes to query perf itself, the numbers there and the diagrams kind of speaks for itself. The dark blue columns in this particular graph are the execution time for a group of queries which were running on that 3 billion row table. And the light blue lines, the ones which are smaller, it's easier to visualize it that way, are the equivalent timings for the same set of queries when running on the table with a clustered column store index on it, plus a few additional non-clustered indexes. So the key point I want you to take away from this slide is as follows. SQL 2016, we enable you to combine these two worlds, right? You have these massive reporting type queries, which have always been supported by the column store indexes, but we also allow you to now do point lookups using traditional non-clustered indexes, all at not too much of a delta in terms of storage. So you can get very efficient storage usage as well with the column store indexes in 2016. Now all of that is good, and by the way, the charts that I showed you are from actual customer labs that we did. We did this with a real world customer, and those numbers are from that actual customer engagement. So it's not something we are making up for this particular demo. So all that was good. Now imagine that you're coming in from SQL 2012 or from an even older release of SQL, and you have this huge data set, billions of rows in that one table, and you want to convert that to a column store index. One thing we still don't have is the ability to create a column store index in an online fashion. What this means is when you do a create clustered column store index, for example, your table is unavailable for the duration of that operation, right? You can imagine that's not always acceptable, especially if you're in a hybrid operational analytics type scenario out there. So this proved to be a challenge for a couple of our customers, because not all DW workloads can be, you can't take a downtime in those workloads. So let's walk through how we would have done this earlier. If you have a table which has millions or billions of rows, we are hoping that you have partitioning in place, because partitioning is one of those key building blocks when dealing with very large databases. So let's imagine that we have SQL 2014 or 2012, and you had to convert this table to a column store index. You would typically end up doing this partition by using a set of insert select statements, and maybe you would parallelize them externally by running multiple commands, each of which is saying, oh, let's get the data for year 2011, for the year 2012, and so on. So you would parallelize them externally, and each of those arrows there is one command. Imagine that each of them is a session which is running a command. Now, insert and select in SQL releases prior to 2016 is a single threaded operation. That means this is going to be bound by resources, primarily I/O, because you're going to be hitting the log and you're going to be eventually writing those records back to disk as well. So this would be a very slow operation in some cases when you have, for example, I/O bottlenecks in the system. Now, fast forward to 2016, where one of the key benefits we have, I mentioned this briefly in compatibility level 130, is the ability to parallelize your inserts. This is very cool because now you can fully push the capabilities of the system, provided you have no other bottlenecks. Let's say you already have an I/O bottleneck, then chances are this may or may not help you all that much. But imagine that you wanted to leverage this capability to push data into a table with multiple threads at the same time. So here is what we could do. We could start off multiple such insert select statements, but in order to get the parallelism in the insert, there is a gotcha. The gotcha is the fact that I have to lock the table using a tab lock hint, the target table, that is. Now imagine what that would do to our external parallelism, right? We are trying to load data into multiple partitions, but we have to use a tab lock, and that effectively reduces us to an even worse situation, because now we have a serial operation through and through. So this came up with one of our customer engagements, and here is what we did in that case. We used a set of staging tables. Now, staging tables and partitioning, hopefully you connect the dots, because eventually you can switch those staging tables into the partitions and you're done with your load. And what we can do with each of those staging tables is we can use this parallel insert select mechanism, which is a very powerful way to push data in at high rates of throughput. So that's exactly what we did to work around the requirements that the customer had in terms of minimizing their data load time. Now, this is not truly online, but it does reduce the data loading time considerably. And if you take a look at the actual outcome, let me just flip to this slide. So this is again from a real world example where, remember the 3 billion row table that we talked about? So you can see the progression of tests out here. So the red columns that you see out here, the red bars, are the behavior with the old behavior. That is the performance with the old behavior, where we were doing single threaded insert selects, but multiple partitions at the same time. So the first set of bars there is when you're doing one partition at a time, which is like you go serially through the different years that you're loading data into. And as we ramp up, so we have 4, 8, and 12, that means you're loading 4 years worth of data or 8 years worth of data at the same time. One of the key things we want to tell you is that if you look at the first one, where we are just loading 1 year's worth of data at any given time, the blue column there is far faster, and that's because of the parallel insert operation. All right, because within one session, one command, I have 8 threads potentially driving data into that table. However, as you ramp up your external parallelism in the form of these different connections, you will start seeing the delta between these two approaches is narrowing, but it's still much faster to do it using a parallel insert in 2016. So again, the talking point here, and the single thing if you want to take away from the slide deck, is parallel insert select works great, especially when you have just a raw comparison between one connection doing serial insert select and one connection just doing parallel insert select. And the other talking point here is, as you ramp up overall concurrency on the system, and you have lots of these parallel inserts going on, you may start hitting some system level bottlenecks. A very common bottleneck we found was allocation bottleneck. So if you just had one data file, for example, in your database, you'll quickly find that that becomes the bottleneck, no matter how much parallelism you get through parallel insert select. Okay? So let's take a quick look at a demo. We'll do that in a minute, but there are a couple of things. So let's just look at the demo and then come back to a couple of other talking points. So here we have a very simple setup where what we're going to do in this script is we're going to set up two tables, one with which has a set of columns. We're going to dump in a bunch of sale records, and we're going to create a column store index on that. This is a clustered column store. Later we're going to insert rows into that table, but you notice here this is the classic insert select. There's no tab lock hint, if you notice. Okay, so this is classic serial insert. And let me just do this real quickly so that we can see execution plans at hand. So we've created the table, and for convenience, I'm just going to show you the estimated plan out here, and I'm going to zoom in this one. So you see this is the column store index operation, and as you can see, it's just using one thread. This is a serial plan, as we call it. Now, when you run this on this particular laptop, it's going to take you a minute or thereabouts. You'll just you'll have to kind of believe me for that. Now, let's see what we can do with this new parallel insert select functionality. With parallel insert select, the way you do it is you use this tab lock hint on the destination table, and you also have to be in compatibility level 130. Now, again, very quickly, I'll just show you the estimated plan, and then we'll actually see how fast this goes. I hope you can see this little parallel operation out here, right? So this is the new parallel insert functionality, and it works great for column store indexes because each of those threads which is active in this parallel insert is actually creating a row group on its own. So for convenience, we're just going to run this, and this takes around 20 odd seconds on this machine. And while that's running, let's take a look at some of these other practical considerations. One of the other gotchas, and this is again from the real world, parallel insert select is great, but then there were customers who were actually trying to load parallel into a table which has an identity column. Now that identity column actually ends up tripping parallel select. When you have a target table which has an identity, or you're using a sequence object to populate some identity type values, just be aware that parallel insert select is disabled in those cases, right? So anyway, let's take a quick look. So this this operation took, which was taking over a minute in a serial plan, is reduced to 17 milliseconds, 17 seconds on this machine. So this has a good SSD, so it's pretty fast. But imagine if you were doing 20 of these at the same time, you may eventually hit some bottlenecks on the data file. For example, you just have single data file, you may still have some bottlenecks. So remember what I said, which is you may fix one bottleneck, but then you may end up running into other bottlenecks. So let's take a look at this this other gotcha that I was mentioning. So we have an identity column in this table, so you can see that there, and we're going to, we've already created that, that's fine. So we're going to try to insert into it. Now notice, we've got the tab lock hint, so ideally we would expect parallelism, right? But that is one of those gotchas that you have to be aware of. So again, for convenience, I'm just going to show you the fact that this is a serial operation now, and as compared to that, when we use a workaround, and this is a fairly acceptable workaround, the workaround involves first of all, you have to simulate an identity insert. You turn that on, and the workaround involves basically using window functions. Any of you used row number before? Right, couple of you. So row number, rank, all of these are brilliant in terms of the capability they bring to the table. And here we are using row number to kind of simulate an identity column generation. This is a very powerful technique, and I will show you the fact that when you Let's take a quick look at the plan. I just want to point out a couple of things here, and then we'll actually run it. Now, you see this little operation here, window aggregate, that's actually the row number. And a couple of things, you notice it's running in parallel, that's a good thing, but there's also a very powerful capability. Remember in the compat level 130 slide, I was talking about batch mode execution for window functions. This is new. Again, it's available only to you if you have a compatibility level 130. Okay, so if you had any other compat level, you couldn't get the batch mode execution. So all of this put together adds up to a very efficient mechanism of inserting into this table. So the identity insert, you saw it's the same amount of data. Now this goes into a heap. This went into a heap table, which is why it took a lot lesser than when we inserted into a column store, because then we have to compress the data as well. But you can see that it's a lot faster than the 1 minute that it would have otherwise taken with a serial plan. Let me quickly go into there's another demo I want to show you, which is around SSIS. How many of you use SSIS to load data into SQL? A lot of you, right? So you must be aware of this next tip. What we have here is a very simple example of data flow task. And this data flow task is not doing anything complex. It's just taking data from one table and dumping it into another table. And both the tables have column store indexes on them. The difference here is in the way SSIS handles batching. And the key point here I want to mention is the fact that when you are inserting into a column store index, there are two stores that you could potentially end up where the data could go. There is this super compressed store, which is what we call as compressed row groups, or if you're trickle inserting, let's say you're just inserting a few rows at a time, right? Like more of the operational analytics type scenario. Those inserts actually end up going into something called a delta store. And the delta store is actually a conventional table. It's actually like a B tree, a traditional index. It's not one of those super compressed row groups that we have for the rest of the column store. Now, why does this matter? When you are loading your data warehouse, you are loading it so that reporting queries can eventually come back a lot faster, right? So the objective when you're loading data is to make sure that most of your data, if not all of it, lands in this super compressed row group, which is the column store data structure that we intend to use. Now, this is the gotcha that we found with some customers. They were using the defaults within SSIS or using an older version of SSIS, such as 2014 or 2012. Now, when you're dealing with SSIS, there is this property which you must be aware of, which is called batch buffer size. So I just want to quickly highlight this out here. You see this is called the default buffer size, and that number there is actually 10 megabytes. That's the default. You can bump it up. You can bump it up to 100 megabytes. Now, what does this mean for you? If you have an especially wide table, you're going to run against this limit very soon, right? Because you're going to pump in a bunch of rows, SSIS is going to batch that up, and then you hit this limit. Now, when you hit the limit, the size of the buffer will dictate how many rows effectively can you cram into one operation that you send to SQL Server, right? And most likely, you're going to end up with a number which is below the optimal size for column store inserts. And that magic number is actually a value roughly around 100,000 rows. Anything which is that number, which is 100,000 rows plus, will directly go into this compressed state. Anything below that will go into the delta store. So it's not that efficient. So let's see this in action. And to demonstrate this, what I'm going to do is actually show you the backend, which is SQL Server. We're going to observe that with extended events. So let me quickly switch to this script. And I have an extended event which I've set up ahead of time. What this is going to do is document each of these statements which are executing behind the scenes. And let's quickly go and watch data live for that particular extended event session. So you'll see some other commands showing up there. I'll zoom in and show you the outcome in a minute. But let's just run this really quickly and take a look at how the defaults look. And then we will repeat it with improvement, which we have introduced in SQL SSIS 2016. So while that is running, let's just quickly talk about what this results in the backend. So we have our extended event session running. And if I do a zoom, and hopefully that works, we'll use a static zoom instead. So here you see the statement completed, and you'll see these funny looking commands, insert bulk. Insert bulk is not a valid T-SQL statement. It's actually what the server records behind the scenes whenever you use a BCP command or SSIS, which is internally using an API to pump a lot of rows quickly into SQL Server. The other thing you must keep in mind here, and this is the key point. Look at the row counts. The row counts are 9,000 odd rows. Where do you think this is going to land? It's going to land in the delta store, right? Because it's not above the threshold that we talked about. You let this run to completion. I'll just kind of close this for a minute. And one of the things you will notice is the amount of row groups that we get on the back end. So that is completed. Let's stop that package for a minute. Go back to SSMS. I want to show you how this looks on the back end. So there's this very powerful DMV which is provided to you, which allows you to sniff into the internals of how this has been set up on the back end. Recall that we had 9,000 odd rows, so it was all going into something called a Delta store. I need to switch to the right database. I'll do that in a minute. And I just want to focus on one thing here. So we have this row group which is in an open state. So this is kind of the state where you have data in the Delta store, so to speak. Let's repeat this again with the optimization that I referred to. And the optimization is right here. So you have this new property which is called an auto adjust buffer size, and this is new to SSIS 2016. It's important that this plays well with SQL 2016 column store. And what that does basically is it allows you to bump up or automatically adjust the size of the buffer depending on what you have set as your batch size. And in this case, let me just quickly show you how that looks. So when you look at the properties of this particular data flow task, we are pumping in approximately 1 million rows at a time. Now, when you run this, let me just start the extend event session again, sorry. And you'll see the proof, as they say, the proof is in the pudding. So we'll just let that go again. And okay, so we've got that started, sorry. We'll just view data live. And we'll let this task run, which is the one with the auto adjust batch size. Where's the execute task? So while that is running on the back end, you will not see the frequency of insert bulk commands that you otherwise saw earlier. You will at some point in time, you will see a single bulk insert bulk command with 1 million rows in it. And that's really the proof of the pudding, where we want to reassure you that with that automatic adjustment of the buffer size, we can actually start loading data straight into the compressed row groups that we ideally want to use with column store. So that's going to take a few seconds. We'll just wait till that completes. And then at this stage, here is the proof that I wanted to show you. So you see here there is an insert bulk command, but look at the row count. So this is exactly the 1 million row mark, and this means that our data has landed into the compressed row group segments. So this is an important tip, and it's a very simple tip if you think about it. So if you're using SSIS, just be aware of this improvement which has been driven in SQL SSIS 2016, a very, very useful thing from a data loading perspective. So let me just switch back to the presentation and walk through the rest of the talking points. So a couple of quick tips for you. So remember, this parallel insert thing is great, but remember some of the gotchas that I walked you through as well. Couple of other things when you're using merge statements, and merge statements will typically use a key to identify which rows need to be updated, deleted, or inserted. Make sure that you support that with a non-clustered index. And in some cases, you may actually have to hint the query plan that the merge statement is using to force that non-clustered index to be used. We have a lot more on our blog. So if you actually go to aka.ms/SQLcat, you will see a lot of the stuff that we are talking about in this deck explained in great detail. We showed you the SSIS tip. There are a lot more tips on parallel insert select as well, which you can see in our blog, at our blog out there. You saw the demo. I'm going to shift gears slightly to a very interesting scenario. This is not particularly to do with column store as such, but this was a scenario around troubleshooting performance at extreme scale. Okay? So we had a customer in our lab last year, and they were using memory optimized tables and native compiled stored procedures, all the stuff that you've heard about which enables extreme OLTP scales. Now this customer was running a workload which was ASP.NET session state workload. So it's an extremely chatty application. It's dumping millions, not millions, but close to 1 million batch requests per second to SQL Server. So we were in the lab, and they had a workload which was on 2014. We were migrating them to 2016. Everything was looking great. We are achieving numbers which were twice the throughput which we could achieve on 2014. But we were still not satisfied because our goal was to get to 1 million batch requests per second, and we were somewhere around the 600,000 mark. So we started troubleshooting what's going on because the CPU in this machine is pegged at 100%. and we really wanted to know what's going on and find out the internals. So we started to look at spin locks, and yeah.
So Arvind, why spin locks?
Okay, so we started doing our due diligence, of course. So we didn't directly jump to the spin lock stuff. And by the way, hopefully you know what spin locks are, or if you don't, there's some great material on our blog. I must confess, I'm touting my blog a lot, but then the blog does have a lot more write-up on this stuff. It's a lot to talk about. But why spin locks? So we did our due diligence. So we went through the gamut of troubleshooting. We looked at extended events to see if there is a pattern which we could isolate. We looked at performance counters to see if there is something in terms of a resource bottleneck at the system. And eventually what we concluded was that there is a bottleneck at the large number of concurrent sessions that we have. And this was on a 144 CPU machine, so a very, very big box, that the spin lock was actually the one which was causing this problem. A spin lock, for those who don't know about it, is a lock at an internal level. It's a data structure that SQL Server uses to protect access to other things. In this case, it was trying to protect access to something called a metadata cache. So I'm going to very quickly demonstrate, and again, as I said, this is involved, but we'll do a very quick walkthrough. So we used a couple of tools, and the tool which we've used, many of you might never have seen this tool before. It's called the Windows Performance Analyzer, and it's part of a Windows Performance Toolkit. What this allows you to do, what this tool allows you to do, is effectively zoom in to exactly the piece of code which is consuming CPU resources on a system. I'm going to zoom in so that you can get a better view on this. And as you can see in this box, we were close to like 100% CPU usage. SQL was using around 70% of the CPU, and the rest was actually the load driver, the test application. And the thing I want to highlight here is the fact that one particular piece of SQL, and that's the spin lock right there, was using up a good 32% of CPU time on that machine, just that one piece of code. So what we did was we started looking at how we can improve this. And this was way back when SQL was not even released, all right? So we did our baseline experiments out there. We took a good hard look at how we can improve this. And I'm glad to say that in SQL 2016 Cumulative Update 2, which we just released earlier this week, we've actually implemented an improved version of that spin lock, which doesn't have this much contention. So the key point we want to drive here is SQL is constantly being updated. Our cumulative updates today have the same level of quality control that earlier you would have with a service pack, for example. And this improvement, which was detected at a lab, has finally made it into the product. And the outcome for us is fairly significant. Let me just show you the improvement that we could gain with this reader-writer version of the spin lock. So this is a graph which shows you pre and post. The line which is out there is throughput. This is the number of batch requests per second we could do on the left with RTM, with the product as it was released, and the one on the right is with cumulative update 2. So we had an improvement of around 13%. This is from a synthetic test, and we weren't even pushing 100% CPU in the end. We were around 72% overall. So that means we can do a lot more if we had adequate load for that system. And the spin lock contention, which is the orange bar out there, is completely gone away in CU2, right? So the key message we want to leave you with at this stage is don't wait for a service pack to come out, because SQL is being constantly updated, right? So we do listen to your feedback, we do make changes based on actual observations, and here is living proof of one of those things, right? With that, I will hand off to Denzel to take you through the exciting world of in-memory OLTP and temporal tables.
Thank you, Arvind.
Thanks.
Okay, so again, there are some resources on the in-memory OLTP related content on the right. We're going to talk about some customer scenarios around this. Just for those who are not, how many of you have worked with memory optimized tables or have at least heard about it? Okay, a good chunk of you. So good. You know, I'm going to cover just about 2 minutes on an overview and then dive into details. So the core goal of in-memory OLTP or memory optimized tables was for workloads that have high throughput and low latency. And the way we achieve that is with lock-free and latch-free architecture. And so we don't acquire any locks or latches in any of the memory optimized table code. So the low latency is achieved in two ways. Effectively, data is memory resident. That's one way. And then the query with natively compiled stored procedures. So every table is compiled into DLL, so we know where the data actually resides. And if you have natively compiled stored procedures, the procedures themselves are compiled into a DLL. That, again, knows where data resides, bypasses multiple layers of the storage engine and query processor and so on and so forth. So you can achieve high scale with that. So, and it's integrated into SQL Server, so you have effectively three engines now. You have row store, column store, and then memory optimized tables as part of the same engine. And you're going to see as we move into temporal, we can mix and match those in various scenarios. So that's the, so this is a actual customer scenario again, where we did a lab pre-2016, and there's a case study published on them. Where they were upgrading from SQL Server 2012, and they had a trading system, and they couldn't keep up with their peak load. So as you can see on the first chart, that was the 2016 time to process 250,000 orders. And the second graph, or second bar, is 2016 applying in-memory OLTP to the same workload, with the time to process 250,000 orders is significantly less than 2012. And the third chart was adding temporal, and I'm showing you this result because we'll talk about temporal. So temporal hasn't really added much of an overhead, because they wanted to be able to actually time travel through states of their trading orders, right? Who made the change, when was the change made, what status changed, so on and so forth. And then, so that's the time to process this 250,000 orders, which was the peak period. Then you have average execution times. As you can see, those also dramatically dropped. It's not only that they dropped, and those are three different distinct business processes, the blue, orange, and gray. All of those significantly dropped. It was not only that they dropped, it's the variance that they had under peak load was very predictable. There wasn't much variance under low load or peak load. As you know, on disk tables, as you ramp up workload, often you hit bottlenecks, as you ramp up, your workload. So one of the key considerations when you actually upgrade to memory optimized tables is making sure, many people think, okay, I've heard about this memory optimized tables. I'm going to lift every table in my database and hope I achieve this, 30 times gain. And so it's very important to make sure that the tables you lift to in memory actually are the ones you have contention which is addressed by memory optimized tables. So we said it's lock-free and latch-free. So you have tables that have locking or latching as a problem, that's a target candidate, right? So first step is migrate the tables only and test with your current T-SQL code referencing those tables. Don't move the procedures to memory optimized. And then the second step is potentially to identify that performance critical code. Natively compiled procedures do have some T-SQL surface area limitations, so I won't go and convert every procedure to memory natively compiled. It's the ones which are frequently run, the 80% of your executions, if you will. Those are candidates for natively compiled. And so it's a staged approach, and you might have a couple iterations on it. Couple things to remember is, when testing in particular, that you have to test at scale to see some of these benefits. If you test at low scale, you might not hit the contention that you would otherwise hit, right? So as devs in particular, you look at this chart and you see at low scale there's hardly any difference, and as you ramp up scale, the time for the on-disk workload exponentially increases, whereas the memory optimized table is pretty linear as scale goes by. The other thing is I/O latency. A commit still has to adhere to ACID properties. So a commit still has to be flushed to the transaction log. So if you have a lot of transactions which are small in nature, at commit time, we still have to persist that record to the log. Right? So that's important. And network round trips do matter. Take an application which starts a transaction from ADO.NET and has multiple statements as part of it. When you're talking of a micro, transaction or statement completion time of microseconds, your network latency round trip might outweigh kind of the time to execute a single statement. So round trips do matter. For the log latency, if you've not seen Lindsay's presentation on persistent tail of the log improvements, go watch that, because that's a new improvement which is in preview on SQL 2016. So the lessons learned. The first one is not a new lesson, but it's something that we've seen continually people run into. There are two types of indexes, non-clustered and hash indexes, and there are use cases for both of these. Right? Non-clustered indexes are used for range lookups. They're just like a non-clustered, similar to your non-clustered index on on-disk tables, except that they are not bidirectional. So if you have order by column ascending versus descending, you might need two if both are frequently executed. And then there are hash indexes which are very efficient for point lookups. But they have a concept of bucket count. And when you do a match, the whole key is hashed. So if you have an index on first name, last name, your predicate, in order to use the hash index, has to have the whole key matched. So that's one thing. DML operations on in-memory tables. So, one of the use cases of in-memory tables is to be used as staging tables in an ETL load. So memory optimized tables can have no logging, schema only, or can be fully durable. And so they're touted a lot on the ETL side. And they're great if you're doing a dump in a staging table and transferring a bulk of that over. But remember that those plans are serial. So if you're doing a lot of data scrubbing and aggregation where parallelism may benefit that ETL, a memory optimized table might not be something that will be beneficial as a staging table. So it's the log bottleneck versus the throughput with parallelism trade-off. So in some large workloads, we've tried these in the ETL pipeline, and they haven't worked as well as maybe a heap. So beware of that. And the last thing is validations. The locking model for memory optimized table is optimistic concurrency. So at the commit time, you have to validate things like constraints, right? So 2016 introduces foreign keys, or enables you to define foreign keys on memory optimized tables. But at commit time now, if you look at this delete statement, it's a delete from a single table. Yet the query plan has reference to two tables, the master table and the child table. Right? So at commit time, validation has to check that you have not violated the referential integrity, for example. And so indexing is key for that, because otherwise you're going to end up doing a scan on kind of the child table in order to validate. So if you have foreign keys, ensure that you have appropriate indexes on those foreign keys. There are a lot more details in a repro of this in the blog post posted. So another big difference that we've seen from an operational perspective from DBAs is log truncation difference. So there is checkpoint which runs on any SQL database, and if you have memory optimized tables or file group, you also have the checkpoint related to that, which is the hackathon checkpoint. And that's a size-based checkpoint. So even if you back up the log, but you haven't hit this 1.5 gigs log, I mean, you won't be able to truncate it. So there might be instances that you say, I've just backed up my log, but why has the log space not cleared? If your memory optimized tables, just realize it's a size-based checkpoint, and 1.5 gigs has to be filled up before actually you can truncate it. So there's a slight difference here. It's not very relevant anymore if you're on CU1 or later. There's a difference in how this worked on RTM release bits versus CU1. In RTM, we had this concept of large checkpoint where this threshold was significantly more, and it was designed for some higher scale, but we've seen that we've not needed it even in our high scale scenario. So that behavior has been reverted. Again, there are details in the KB articles. I won't spend a whole lot of time on that. So let's look at some demos. So I'm going to create a database here. Oh, thank you. Going to create a database. As you can see, we have a memory optimized file group here. The database is created. I am going to create a table, which is a durable table, and a memory optimized table. And the only reason I'm creating this stored procedure is to populate data, so the contents are not, really relevant. So as you know, when you have a full recovery model, in order to start the log chain, I'm going to checkpoint and back up the database and back up the log. So this is a normal, occurrence. So I've done that, and we're going to look at log space for this database. As you can see, it's hardly used here. It's barely used. So it's a new database. If you look at the checkpoint file pairs, which is the storage for memory optimized tables, you will see that only one of them is actually active. Only one data file is actually active. And so I'm going to go ahead and start inserting some data. So I'm going to execute this in a transaction and let it rip. It'll take about 10-15 seconds. And while that is going, I will go to another window. And just execute all three of this. So the first statement is the log reused weight description, which is how in sys.databases you know your truncation point. Effectively, what is blocking my truncation, if you will. The second one is the space, which SQL perf log space, which tells you how much of that log is actually consumed. So if we look, it's 30% right now. And the third one is looking at checkpoint stats, which tells me since my last checkpoint, how much log have I generated. And so in this case, it's 448 MB. So as you can see, one more time. So as you can see, about a gig of log has been generated since I started this. And so what we're going to do is we're going to do what a DBA. So say I have a backup of the log here. I'm going to back up the log. So I'm backing up a gig of log. But even after the backup of the log, you're going to see that this in-memory OLTP is still using 68%, right? And the log has not been truncated. So you would expect this to actually drop after a log backup, from that perspective. So you may have to, in such cases, just be aware of it. And so a checkpoint in this case, if we issue a checkpoint, couple of things you're going to see. The checkpoint files, the active goes up to at checkpoints we are actually writing that data to the data files. So that's one thing you're going to see. And the second thing, if we go to this query, did I not back up the log? I only hit checkpoint, sorry. I have to back up the log too. If I go to this file, then the log is purged. You see it's hardly used at all. So that's one thing. So let's look at the second demo in terms of indexes. So again, I have this database already. So I'm going to just create a sales order header table. And so a couple of things. I have the hash indexes here, and I have non-clustered hash indexes with a particular bucket count. So I create these. Would help if I switch. So again, so I have sales order ID, which is the primary key. I have a hash index. I expect point lookups. And I have a status column also as a hash index here. So I'm going to insert about 132,000 rows in this. And we'll see the time. This should take roughly about 10 or 15 seconds. And we're going to see some distribution of hash buckets and if they're empty or not. So let it complete. So this was roughly 11 seconds here for this insert. So a couple of things I'm going to, this query effectively just gives you the row count and how unique each of these index columns are. So I'm going to run all three of them, and then we'll dig into some of the results. So as you can see, the primary key here is pretty unique. So these are unique values. So effectively it's a primary key, so it's unique. So in the IX order sequence index, well, you don't have these are the number of rows, but these are the number of unique values. Well, I mean, it's not totally unique, but you'll have some collisions, but not that bad. But in the IX status, you have only 8 unique values effectively across all the 132,000 rows that you've inserted. So there is a good DMV here, which is, or catalog view, DMDB XTP hash index stat, which actually gives you how many buckets you have empty and what's the collision. Because in a hash index, just like any hash index, you have the buckets and everything is linked off a bucket into a chain. So if the chain gets too long, you have to traverse the chain in order to insert an element. So in the status case, you have the total buckets of 8, but 4 out of those 8 are empty, which means there are only 4 values, if you will. 50% is empty, but the average chain is 32,768. So each time we insert a row, actually, we have to traverse that chain. So this is not, if you don't have a value which is very unique, status columns and such, non-clustered indexes are the way to go. Hash indexes are not the way to go. Because they allow more of a range scan. Any predicate with that clause is not really a point lookup if it has very few unique values, right? So this is the alter index support, which is again new in 2016. So I drop that IX status index and I add that back as a non-cluster. I don't have hash in this definition. I delete this the rows from this table, and I insert that same 132,000 rows. And that's done in less than a second. I mean, that's the impact it can have, of not defining your indexes, correctly. So let's move on. We have a UDF case. Okay. So we also have natively compiled UDFs in SQL 2016, scalar UDFs. And that's an easy way, actually, if you have scalar UDFs. So first of all, if you have scalar UDFs, a lot of your processing, if you use them in predicates, is row by row. So for every row, you have to invoke the UDF in certain cases if you use it in a predicate, right? If you can convert that to a TVF, that's the preferred way to go, because then it can do a set-based operation, right? But in many cases, you can't. And so natively compiled UDFs can help in such cases even optimize that to some extent. So let's take this UDF as an example. This is an airline company, where based on the carrier, you have a amount of discount. So it's pretty simple. You pass the airline and the origin and the fare, and you have some discount metrics around it. So I create a UDF. Okay, and I will create the same thing as natively compiled, so no difference. The only thing is with native compilation schema binding. So this is the preamble for any natively compiled stored procedure. So you have to specify with native compilation and schema binding, and the begin atomic block with is necessary. So I create the same code as that. And so I create this. And now let's look at the time taken for each. And I'm doing a single execution. So the power is not in the single execution of it. But think of a table with million rows where this is executing once per row, right? So I execute this. And if we look at the messages tab here, that is 252 milliseconds versus 94 milliseconds. More importantly, CPU, which is at 219 seconds versus 94 milliseconds, right? Extrapolate that off a workload which executes this, very often, and you'll have a huge improvement from a perf perspective. The next easy target, if you will, is temp tables where you have latch contention type issues. So let's look at the typical proc, and maybe not a typical proc. This is an oversimplified, procedure where, but how many devs do we know use a temp table just because they don't want to write a complex query? So they take a little bit of information, put it in a temp table, and then, use that later on in the proc, right? So, so I have a do some work proc, and what I'm going to do is I'm going to create this. I'm going to run a workload here. okay? And I have a monitoring off of DM exec requests. And I can see if I run DM exec requests, a lot of my contention is page latch EX, right? And this is not your traditional GAM SCAM contention. You know, GAM SCAM, you say, okay, add number of files, so on and so forth. So this is 120. If you look at 120, it's actually one of the system tables. So you don't have explicit control over. So you have two options, right? Change your code, figure out where this is being used in your code, or you know what I mean. That's the only option, or move to memory optimized in this case. So you have that contention. If you look at specific resources we are waiting on, it's effectively this page 120, which is a system table. And if we look at the weight type, because I've cleared the weight stats before this, all my weights in this workload was latch contention, right? So it's huge amount of latch contention, you know, here. So, you know, do I have many tempdb files? Yes, it's on an 8-core box. I have, you know, 8 tempdb files, so as many of the cores. So I followed the best practices. It's not 8. What I'm going to do is I'm going to create another procedure which is the same equivalent, except I'm going to use an in-memory table type. So what I do, what I do here is for the same temp table, I create a type. Note, you have to create a type with memory optimized equal to on. So what that means is you can't blindly, you don't want to create this for executions that are single executions or single use of the temp table. Again, it's your critical path code, right? If there's a procedure which is executed often, makes sense, because you have to know the structure, right? So I create a type here with memory optimized equal to on. Type already exists, okay? And then I create the procedure which does nothing but just inserts into that type instead, right? And execute it to make sure no syntax errors. And as you can see here, this workload took a while, more than a minute and some, right? So I'm going to repro in mem. And if I go back to my, you know, waits period, I don't see, you know, wait type contention. Actually, at this point, I'm probably running out of threads because I don't have a delay. I'm pounding the server, but I don't have any wait type in itself. And if you look at the workload, I mean, that's done, you know, that's pretty much done quick. So that's a quick way, without having to change much of your code. You just change this object to, you know, a memory optimized, you know, table type, and you can, you know, benefit from it. Okay, so I will move on in the interest of time. 5. Okay, so temporal. So we talked about column store, we talked about in-memory tables. How many of you have actually been exposed to temporal or worked with temporal at all? Okay, so even fewer cases. So just a brief overview of temporal. Temporal allows you to time travel through the data. So you have the concept of a current table and you have a concept of a history table. Every insert goes into the current table, so there's no history impact to that. Any update or delete actually moves the old version of the row to the history table. So you have an audit trail pretty much from that perspective for every status of your row. And from the select perspective, if you just do a select from the current or history table, you get only data from that current or history table. But if you do select with the as of clause, which is more of the temporal time travel, depending on what you specify, you get a union of what if that data is in the current table or history table or a combination thereof. The cool part is this history table can be anything. The history table can be you know, row store, page compressed, column store. You know, so there's flexibility. It can have different indexing than your current table. So your current table can be optimized for more of your OLTP type workload, but the history can be optimized more for how you want to report on those queries, right? Or look at history. So how cool is it that you can do temporal tables not only with on-disk tables, but in-memory tables as well? So we have an in-memory equivalent for this. So what happens here is when you have temporal on an in-memory table, you also have an in-memory internal table And that's effectively to take out the shock. Why would you use in-memory OLTP? For fast, low latency type workloads. So if you had to actually, as part of the same transaction, move the version of the row to an on-disk table, that low latency might not be so low latency. So you have the in-memory internal table because of that. So on an update delete, as part of the same transaction, that old version actually goes to the history table. And asynchronously then, data is migrated from that in-memory internal table to the actual on-disk table. And then a disk-based table, again, can be a combination, it can be page compressed or can be column store indeed. So one of the popular scenarios in kind of the validation of workloads was this hot-cold pattern, right? So part of in-memory table dilemma is always, okay, how large do I get that table to be? So you have only limited memory. It has to be memory resident. And so you either have to have some way of archiving the data off as it grows if you don't want it to grow fundamentally. Or in some cases, this hot code pattern has been fairly popular in both telemetry type instances as well as order management from a trading perspective, where active orders are in your current table and then closed orders move to your history table. Similarly, in telemetry, the current table is there for the insert activity, but then you can have batch deletes. A delete from the current table moves the previous version of the row to the history table. So the data is there. So this enables the memory optimized table to be smaller. Again, log IO is very important. A commit is still a commit. This is still part of a transaction. So your log IO actually will matter even potentially a little more, because now it has to log both the delete from here and the insert there, or the update is the insert there and the move of the row. So that's that. Indexing history table. Indexing history table is key. If you take the shortcut and create a temporal table with the minimal syntax, there are only a default set of indexes created on the history table. Think of it like replication. When you do replication, only primary key is transferred unless you want additional indexes to be transferred. They're not, right? So what do you index the history table depends on your query pattern. Again, I said, if you're doing singleton type lookups, so for example, in a trading system, if you're doing select or looking at history based on an order ID, for example, which is more of a limited set of data, then use page compressed. If you're doing aggregate type queries across all the history data, use column store. One limitation, if you will, on the internal history table is you can't define the internal in-memory history table. And so it has only one default index right now, which is that sysend time, start time. And so let's jump into a demo. 6 minutes. Quick demo. I've created this table. So this is the easy syntax to say, okay, I'm going to create an employee table with system versioning equal to on makes it a temporal table, and history table equal to employee history, right? And you need two columns which are datetime 2, which specify the start and end of the validity of the row, if you will. So I'm going to create this, and of course, you skip a step, you pay for it. Okay, sorry guys. So much for prep work. Okay, so I created that table, and if I check indexes by default, the only index by default on the history table is valid to valid from. So if you're doing any sort of criteria on order ID or any other indexing, you don't get that, right? So that's one thing. So let's look at the in-memory equivalent. So I'm going to drop this in-memory table. So I have a memory optimized table here. So this is memory optimized. I have a primary key non-clustered index here. I create that. Here I'm creating a partition scheme. I think it already exists. And because one of the best practices would be actually to partition your history table again. I think I skipped a slide. Yeah, I did. So we'll finish the demo and then go back to the slides. So I created a partition. It's already created, so I'm not going to delete it. And I'm creating the history table on that partition. And the reason why is at some point, even your history table, you want to age out information. Partitioning makes it an easy way. It's one of the most underused features, to be honest. So it makes it an easy way to swap out that data and actually archive. So I create that. And then I create my custom indexing, which is what's recommended. So in this case, I'm creating a clustered column store on that table, and I'm creating an additional non-clustered index on top of that clustered column store. So this is where the mix and match of having one engine is awesome. And I'm populating some data before I bind it to temporal. So this is to simulate that data existed before I bind it. And effectively, here is where I set the temporal. So I'm adding in the valid to and valid from columns as the period columns. I'm hiding them. I'm marking them as hidden so that they don't appear in my select star output. And then I'm saying enable versioning. So I create that. And this is a metadata query, which is going to show you the in-memory internal table. This is on Books Online. And the reason is I need the name of this. I need the name of this table in order to show you the indexing. So this shows you the inventory table also has an internal table, which is memory optimized table. And this is not something you can control the name of. So I pick that table and replace it here. And we can see the indexes now on my 3 tables. This is my current table, which is my OLTP table, has only one index. This is my history table, which I created clustered column store. And this is that internal table, which has valid to, valid from. This is the primary key and change ID. And you cannot create any additional indexes on this as of today. We're looking at making that better. So if I look at plans here, really quickly look at plans here. If I hit just the current table, of course I get a nice seek because I have an index. Right? If I hit the history table, right now I don't have much on the history table, but you see that the history table, even just querying the history table, it's a union of the actual history table and that internal table. It's pretty much transparent to you. So it's a union of what is in the history table and that in-memory internal table because they're both considered. But it's also a table scan because there's no index that satisfies the where ID equal to 1. In this case, there's no data really in that history table, from a changes perspective. So I'm going to make about 2,000 changes and run the same query. Oops, that would not help. And run the same query. And you see now, this is where this can actually hurt a little bit, right? So as that in-memory history table, internal table that you don't have indexing support for, grows, and that's automatically actually asynchronously moved when it reaches 10% of the current table. But if the current table is large, 10% can still be large, and so a scan can be harmful. There is a way around that, and there's a way that you can manually flush that history table called XTP flush temporal history. In this case, my current table was so small that by the time I've done this, it's actually moved it to the background. So you see this has moved it to the background. This is not a table scan. The plan has changed fundamentally. But if not, if you reach that situation, there is a stored proc or spec proc to actually move it. I know I'm 50 seconds left on this. So I will, so partitioning is the other demo I had, but partition a table because you cannot delete out of the history table without setting system versioning equal to off. So if you want to archive data, partitioning is a must because otherwise you have to unbind the table, which may be downtime if you're banking on that, audit trail. So that's all I have at this point. In closing, SQL 2016 has been one of the most validated releases, both because that code base goes to Azure first, and there have been significant improvements in 2016. We hope that you have found these sessions useful, and if you want to engage with us, that's the links at the bottom. So I'll be around for questions. Thank you guys for staying for this last session. Appreciate your time. I know we are running out of time, but we'll be hanging around here.
Thanks.